So thanks also for giving me the opportunity to be at this wonderful workshop. I consider myself rather a novice in the field of decision making, and it's just, I'm very grateful to have the opportunity to discuss all these complex issues with people who thought about them for much longer than I did. And one thing that fascinates me about the question of decision making is that decisions are a collective phenomenon. So if you look at a flock of birds here, it's hard to say who makes the decision where to fly. And I think there's a similar situation in the brain. Every neuron is talking to everybody, and it's really difficult to nail down where the flow of information goes along, and yeah, what kind of computations are critical for the behavior output in the end. So I put up this slide from Jim DiCarlo's paper to remind you of the distributed information flow, which already starts right at the retina, already at the first synapses, that the information is spread into parallel channels, and it's even not clear if the information is present in one channel, whether that is used in the end for the decision. And in addition, of course, there's feedback and top-down, which makes things rather more complicated. So that's exciting for theoreticians, but it poses many theoretical challenges and difficulties. I try to summarize these aspects in a more abstract sketch here, and give a little historical perspective of my own. So during my PhD, I basically only worked on neural populations without thinking much about the structure and the sensory input and the perceptual output, or at least not taking them explicitly into account. And interestingly, one workshop on noise in a system, I think it was in Berlin in 1998, actually motivated me for my first study on signal propagation in populations of neurons, which was a talk by you, Mike, and to try to better understand how variance can be used as a signal for signaling intensity signals across populations. And in the end, my conclusion was actually that it is not that useful or not that desirable to introduce noise in the system to do intensity coding. And like Sophie also nicely showed today, there are other possibilities without noise where you can do rapidly transmit intensity signals in populations of neurons. But I think that's something we will discuss later. So then later I also focused a lot on the sensory input, but it was only until Ralf joined my lab that I started to work also on the perceptual aspect and on the question that I will talk about today, mostly of how to infer or how to relate the readout of neural populations to decisions that are made by an organism. In general, I'm quite excited to put everything into one global model at some point. So we are working, or we started to work towards this. Unfortunately, I don't have true results to present here. So, but I think it's important to have everything in mind, basically, to make everything explicit in order to to resolve all these discussions that we have often because we come from different viewpoints. I think that's a major difficulty, that if you want to understand the entire flow of information from the input to the perceptual output, that there are so many aspects that you have to take care of that we often lose one here or there, and then we talk about different things. Okay, but now I start with the introduction for my actual talk. So the main quantities that we will look at is the tuning curves, which define how a neuron responds to the stimulus, and then on the choice probabilities, which give the we have been talking about a lot today already, the probability for a choice conditioned on the sensory on the neural response. And to remind you that this is also always task dependent, so we are preparing the system, and basically the organism is trying to achieve a certain task, and there's objective function where you can measure how correct you are, and there are like psychometric functions and neurometric functions that I won't further mention later. Okay, so the tuning curves are how related to how each neuron is affected by the stimulus, and choice probabilities, the question is how much each neuron contributes to the decision, how much they are related to this question. That's the main question of my talk. Okay, and most of this stuff is published in this paper that came out recently, and I will first present the main analytical result, which gives the connection between choice probabilities, noise correlations, and readout weights, and then I will basically try to explain the implications of this result and how it can be useful for understanding decision making. And then at the end I will become very speculative and so talk about things that may be completely wrong. Okay, so to remind you, the model is really the standard model. We have several neurons with different tuning properties, usually with different preferred stimuli. We have readout weights that are then weight the contribution of each individual neuron and are summed up by some, in this model, by some latent readout variable that is not directly observable. What is observable is only the threshold, or after thresholding the choice whether you decided for one or two. And so there are different possibilities for these weights, and these is what we are mainly interested here to into the question, what inferences can we make about the profile of these readout weights. And so one possibility would be that we have basically a flat readout weights which weight all the inputs from one population with the preferred direction in one pool, the positive weight, and all the others with the negative weight. And alternatively, we can try to do something, say, an optimal readout to maximize the signal-to-noise ratio about the problem here, and then we get a very different profile of the readout function. And the critical ingredient are the noise correlations. So we will often consider the variance between the response of neuron I and neuron J, which will be abbreviated as Cij in the following. And then we will work with covariance matrices, as we have already seen a lot in Bruce's talk. And so for the simple task where we basically have two pools here, we can distinguish the two blocks corresponding to the pool belonging to the same preferred direction and the different pools. And so we can assume different covariance matrices like being constant within pool, or something more empirically motivated, having some limited range correlations that can be measured in a pool-dependent fashion. Okay, and there's also some independent noise which shows up as a ridge in this covariance matrix, which is quite important also. Okay, so the central result of this work is basically a connection between the choice probabilities to the readout weights and the covariance matrix. And so the derivation, I won't go into any details here, is quite lengthy, and it was actually due to Sebastian Gerving, who came up with a cool trick to solve the integrals involved. But the result is very intuitive, and the purpose of my talk is to explain basically how to infer the the readout weights in the end from the choice probabilities. And the main property here is that well, an important quantity to look at here is this CK, which is given by the product of the covariance matrix with a readout vector and divided by the variance of K and term which is basically the variance in the direction of the readout. So this can be derived also as the correlation of the latent readout variable with each individual neuron response. So it's the correlation coefficient where you have the covariance between the noise of neuron K and the readout variable in the numerator, and then we have the noise variance of neuron K in the denominator and the noise variance of the readout variable in the denominator. And the nonlinear relationship between this choice correlation and the choice probability essentially comes from the nonlinear dichotomization of the decision. And fortunately, one can approximate this nonlinearity very well by a linear function. So we check that, and the approximation is extremely good over the entire range. So the deviation is most 5%. And so basically what we need to make inferences about readout weights and the connection with the choice correlations, for that we need these latent choice correlations. And now, since we know the connection between these choice correlations and the choice probabilities, we can essentially work with the choice correlations in the future. So what you measure is choice probabilities, but by this simple formula you get the choice correlation, and there you have the connection between readout rates and choice correlations. Okay, so we now have this analytical relationship, and now the question is, what can we do with it? First, we can prove and generalize earlier numerical findings, and then, and that will be the main focus of my talk is to show when and how readout strategies can be inferred from choice probabilities if the noise correlations are known. And then we also present a test whether the readout is optimal using choice probabilities and single neuron responses alone if you don't know the correlations. Okay, to remind you of an earlier study which basically questioned the possibility that you can infer the readout weights from the choice probabilities. It's a very intuitive model, so you have a population of neurons, but and there's a positive noise correlation between all the neurons, but only a subset of the neurons is read out. And then if you increase population size, then the choice probabilities between these two pools, those which are read out and those which are not read out, actually become equal. And so it's in the limit of large n impossible to distinguish between neurons that are read out and those neurons that are not read out on the basis of choice correlations. So the question is, what can actually be inferred from choice probabilities about the readout? And so this is probably the main slide, and I will walk you through slowly. I try to give you a geometric intuition of the readout, of the connection between readout and choice probabilities. So the central formula here is the choice correlation with the product of the covariance matrix times the readout vector in the numerator, and these two variances in the denominator. And I will write this is for one component, for one neuron K, and we can write this more efficiently in a vector notation. And basically, you can ignore this stuff here more or less. So that's not. These are essentially scalars, and the crucial part really is that the choice correlations are proportional to the product of the covariance matrix and the readout vector. And if you want to understand a mapping like what this covariance matrix does to this readout vector, you look at the eigenvalues of the covariance matrix, so at the principal components. This is algebraically how you write it down if you decompose this covariance matrix into its eigenvalue decomposition. But I will explain this hands-on in the two-dimensional case. Say this is your covariance matrix, your noise covariance matrix with the largest noise in this direction and the least noise in this direction, and this is some readout vector. And now what you do is you decompose this readout vector, or you represent it in the coordinate system of the principal components of this noise covariance matrix. And then you know, basically, if you want to know what happens to the mapped vector after mapping it, you just have to multiply this component by the eigenvector of the covariance matrix. So since this variance is much larger, this component becomes amplified and relative to this component. So what happens due to this mapping is that your readout vector becomes biased and stretched towards the noise directions. Okay, and now we can use this mathematical formalism to look at the effect of arbitrary noise covariance matrices. I restrict here to the case of two choices, again the constant pool choice, and in the case of a very small population of only 18 neurons and a large population of 2,000 neurons. And this black line, the solid line, shows the actual weights, and the red line and the blue dot shows the choice probabilities that are generated by the readout weights. Oh, okay. Good to know. The main point here is that that you can't distinguish anymore between this readout profile and this readout profile, for instance, if you have such a noise covariance matrix, and because the differences basically become attenuate, which is due to the fact that the eigenfunctions of this covariance matrix are they don't vary within pool. They are constant within pool. While if you have a more realistic noise correlation matrix, then you have variations within pool, and this allows you to infer the readout weight profile. So basically, we just have to invert this vector equation to do the inference. That's done here. We need to get rid of this term, so we can only say we can say nothing about the length of the readout vector, only about its direction. And the problem is that you have to say something about the inverse covariance matrix, and so you have lots of small eigenvalues. And so if you look at the inverse, all these small eigenvalues become amplified, so you have really a noise problem here, which is indicated here, which makes inference of readout weights hard and necessarily biased by assumptions. So you have to regularize and you have to make assumptions if you want to infer the readout weights. And if you have to make assumptions, then it's good to be explicit about what assumptions you make. So we have demonstrated that for a case that we consider or try to make as realistic as possible with realistic readout noise with heterogeneous populations, etc., it is possible to distinguish, at least in the subspace of the first four eigenvectors, the readout profile of a constant readout weight profile and optimal readout weight profile. And for the sake of time, I just say here it works. It's noisy, but it works. And so there are two principal limitations that I want to mention. One is that parametric models always lead to overestimation of the choice probabilities. So that was also came up or relates to your talk. Maybe if you make a model of the covariance matrix, then it's likely that you ignore eigenvectors that would also contribute to decreasing the choice probabilities, and therefore in models it can easily happen that the resulting choice probabilities are smaller than you would predict from the measured noise covariance. And the other limitation is that readout weights are not reconstructible outside the bad noise subspace. Okay. Okay, we also have a direct optimality test, and the basic assumption is that you assume the optimal linear readout for the weight profile, and if you do that, as a consequence, the readout profile has to be proportional, or the readout weights have to be proportional to the derivatives of the tuning functions at which you measure. And you can test for this linearity here by plotting basically the choice correlations on the x-axis and the derivatives of the tuning functions on the y-axis, and then you can check whether how linear your data is by looking at the deviations from the linear regression line, and then you can make comparisons that allow you to make tests. So to summarize the results, we have an analytical relationship. The choice correlations are the main tool to make the connection between noise correlations and readout weights. We have a theory of readout weight inference based on this, where we can also say when it is possible and to what extent it is possible to reconstruct the weights. And we have a direct optimality test. And as a remark, we didn't put this in the paper, but the original motivation was actually the work by Hendrikje. So this is very easily extendable to the time domain, so you just have to include time coefficients in your covariance matrices and in your readout profiles, and then you can use the same formalism to do inference also in the time domain about the readout. Okay, do I have more minutes to say something speculative? Okay, I tried to say it in 1 minute. Some speculative comments on the origin of noise. When is large choice probability? So this basically the question is, when is this formula at the order of being constant, so it doesn't decay with n? And there are two possibilities. Either the denominator here doesn't increase with n. So in the independent case, the variance of your readout would accumulate more and more variance, and then this scales like 1 over n. But if you have, for instance, if your readout weights read out only a small subpopulation, then it doesn't matter that you have much more information presented. This will stay of constant order. Another possibility is that your numerator scales proportional to n, and that is usually the case of bad noise. And this might be related to Alex's talk, I'm not sure, not noisy, just strong, and it might also be related to a work that Sak-Pitkov showed at cosine, where I think he concluded that the brain is not wrong, but just noisy, but maybe not. So Alex will clarify that later. And I put Mike here as saying the brain is both noisy and wrong. And so one possible origin is for the noise that you're all familiar with, that the brain needs noise for rapid intensity coding and can avoid common bottom-up inputs. And this would lead to bad noise, and bad noise in the sense that you have a large component along these directions. And then even for optimal readout, the population precision wouldn't be better than the single neuron precision. That's why we call it bad noise, or by Alex and his colleagues call it bad noise. But an alternative hypothesis that I want to put forth is that the brain is probably not optimal, but also probably not that bad. And The hypothesis is that there's paradigm-dependent noise shaping, which means that I think that currently our models miss important aspects of the situation that we are trying to model, and these are likely to induce this type of bad, or two different types, possible types of bad noise. And I don't have solid results to present on this, but it's my hunch that basically if we are more careful about these other things like tasks and adaptation effects in neurons, etc., serial correlations that Enrique might be talking about later, that this will show us that the brain maybe is not that bad in the end. And so I took Sophie's talk as evidence that noise may not be necessary for fast intensity coding. Also, common input does not necessarily lead to noise correlations, and serial correlations and paradigm specifics are I think are a likely source for bad noise. Thanks for your attention.
Yes, I have no time for questions, but while the next speaker is setting up her computer, I would suggest some questions. Or are there none?
Can you elaborate a little bit on what you mean by paradigm specific?
Paradigm specific. So specifically, I mean, so the choice probabilities are usually measured at zero signal, right? But they're embedded into sequences where you have signal before, in order to keep the enemy motivated. And you might have also serial correlations in the responses. And so there might be a correlation with the correlation, the serial correlations of the decision, and in these serial correlations with your future adaptation effects. If you have a paradigm where you actually have a signal before you have the zero signal trial. So it may be that if we explicitly try to random work to change the readout vector before we make the zero signal trial, that these choice probabilities may go away.
One final question? Okay.
What's the correlation?
Oh, in time. So temporal correlation, so like at the neural level, adaptation effect, all kinds of correlation in time, and at the decision level, if you have several trials, one after the other.